Hi guys, greetings of the day. I, Vijay, welcome you to my YouTube channel for learning a subject called Fluid Power Engineering for 5th semester as well as Fluid Power Systems for 7th semester as per video syllabus. If you haven't subscribed to my YouTube channel yet, kindly subscribe. Also click on the bell icon to receive the latest video lectures as and when it is going to be uploaded in my YouTube channel. Now let's start the session number 11. So which is like this. We are going to have a discussion on Lobo pump, internal gear pump and Gerotor pump etc. What is called as Lobo pump? Let us have a figure of the Lobo pump. The Lobo pump operates on the same principle as that of an external gear pump, but has a higher displacement because of very few number of teeth, that is 3 on the each gear where you can see in the figure. Due to this, the teeth are wider and more curved than those found in the regular external gear pump, which we have discussed in the previous session. Now, the advantage of this Lobo pump is that it is suitable for shear sensitive fluids as well as fluid with entrapped gases and particles. But the disadvantages are relatively low pressure and pulsating discharge. Then coming to internal gear pump, this is the figure of the internal gear pump. In internal gear pump, the meshing of teeth of the gears takes place internally and hence the name internal gear pump. This consists of an external gear that meshes with the teeth of an annular as shown in the figure over here. You can observe. The pumping chamber is going to be formed between the gear teeth of the gears. A crescent seal is meshed into the space between the inlet and outlet and unmeshing region of the gears, which you can observe in the figure, where the clearance between the teeth of the annular wheel and the external gear is maximum. In this way, the two inlet and outlet ports are separated while the oil is carried by the gears past the seal. Internal gear pumps are also available in single and multiple configurations. And how does it work? The low pressure oil from the inlet port is converted into high pressure oil and sent through the outlet ports as follows. That is, the internal gear drives the external gear and affects the tight seal where the teeth are meshed. Rotation of the gears cause unmeshing near the inlet port. The cavity volume increases and suction occurs. Oil is trapped within the internal gear and the external gear teeth on either side of the crescent of the seal and is carried out to the outlet of the pump. And the meshing of the gear teeth reduces the volume in the high pressure cavity near the outlet port, which is as shown in the figure of the internal gear pump you can observe. Then one more concept is that is called as reversing of input shaft rotation. How does it going to be achieved? Let us understand it. In some of the internal gear pump, the annular wheel, which is called as internal gear, which you can observe in the figure, is driven with the external gear connected to the drive shaft. But in some types of external gear is driven while the internal gear is connected to the drive shaft. When the external gear is driven gear, by rotating the crescent seal and the internal gear assembly by 180-degree, the shaft input rotation may be reversed. Then coming to G-rotor pump, which is also called as generated rotor pump. Now, one of the most common types of internal gear pump is called as G-rotor pump. Now, the figure you can see, a G-rotor pump combines the features of internal gear pump without the crescent of a seal as discussed in the previous case. In this pump, the inner gear has one teeth less than the external gear and is keyed to the driving shaft. And you can observe the figure, the basic parts or the components of the G-rotor pump you can see. How does it work? Let us understand. As the gear rotates, each tooth of the inner gear is a constant mesh with the teeth of the annular. As the annular has one teeth more than the inner gear, it rotates at a slower speed. Space between the rotating teeth increases during the first half, that is, increasing from smaller to a larger volume, drawing fluid into the chamber. Similarly, the space between the rotating teeth decreases during the second half, that is, decreasing from larger volume to the smaller volume, forcing the fluid into the outlet port. You can observe that in the figure number B, which illustrates the principle of the working of the G-rotor pump. And why the gear pumps are called as fixed pumps? The reason is the discharge in a gear pump is a function of external and internal diameters of the gear, width, and the teeth of the speed. Teeth and the speed of the pump where it is going to be calibrated in RPM. The housing and cover plates are the pressure plates are mounted to the designed dimensions. Hence, at no time for given for a gear pump, it is possible to change the elements of different dimension. Thus, the displacement of the gear pumps remains fixed. The only possibility is varying the displacement by varying the speed of the pump. Then coming to the vane pumps or vane types of pumps, which is also called as sliding vane pumps. The pumps are also a rotary pumps and operates on the principle of increasing and decreasing volume. Increasing volume of the cavity produces vacuum which draws the fluid into the chamber and fill up the space, and decrease in volume causes the fluid to be forced out of the chamber under pressure. In this case, the veins are allowed back to drag a ring generally, which is called as a cam. Then what are the different classifications of the vein pumps? Now there are different classifications based on fixed displacement unbalanced type and the fixed displacement balanced type. In the same fashion, variable displacement balanced and unbalanced are the subclassification. And the important elements of the unbalanced type vein pump are the rotor with the radial and longitudinal slots to accommodate the veins, and sliding veins, which are also called as radial veins, and the stationary circular camering and the housing. You can observe the same thing in the figure which are there here. These are the basic components of the vein pump or the basic elements. Now let us understand how does this vein pump will work. That is the principle of working of a vein pump. The rotor, whose axis is positioned eccentric to the circular camering, rotates inside it, which you can observe in the figure. The vanes, which are freely to slide radially inside their slots provided in the rotor, move outward due to centrifugal force. These vanes make contact with the inner surface of the camering, and the positive seal is maintained between the vanes and the camering. And during one half of the rotation, the volume increases progressively between the rotor and the camering, what you can observe in this figure. Okay. This increase in volume causes the reduction of pressure and is the suction process during which the fluid flow into the housing through an inlet port and fill the void. Now figure A shows the assembled view, whereas figure B shows the principal working of the vane pump. Now as the rotor revolves through the second half of the rotation or the revolution, the surface of the camering pushes the vanes back into their slots and the volume becomes progressively smaller, and this reduction in volume increases pressure and its ejection process, during which the fluid flows out of the pump through the outlet port. And the pumping cycle occurs twice in each revolution in case of a two vane per slot, and the displacement of the pump depends on the width of the ring or vane or the rotor and the distance of the vanes allowed to extend from the rotor surface to the ring surface. The contact between the ring surface and the vane tips result in wear of both ring and the vane tip. To maintain a constant degree of contact, the vane comes farther out of their slots as they wear out. Now we shall have some characteristics. Now out of that, the volumetric displacement of the vane pumps we are going to discuss. Now you can see this is the figure for understanding purpose, where E is equal to E max, that is the maximum eccentricity, where the eccentricity of the vane is 0, and this is the pictorial representation of the vane pump you can see here. Now let us have some terminologies like DC is nothing but the diameter of the camber in meter, dr is the diameter of the rotor in meter, W is the width of the rotor in meter, E is the eccentricity in meter, and Vd is the pump volumetric displacement, that is normally called as theoretical in meter cube per revolution. In the same fashion, Emax is equal to maximum possible eccentricity. Vd max is going to be the maximum volumetric displacement meter cube per revolution. Now, let us understand the same figure where I have eliminated the pictorial representation and I have retained a schematic representation with maximum eccentricity and minimum eccentricity. Now, how we are going to get the volumetric discharge? The volumetric discharge is going to be calculated by seeing this figure. It is going to be defined by the shaded area or the effective area of the displacement of the vane pump, which is given by this formula, that is shaded area is equal to pi by 4 dc square minus dr square. Dc is the cavity, dr is the rotor. Now, this is in the form of e square minus b square. When we are going to expand this can be written like this: pi by 4 dc minus dr into dc plus dr. Now, we are just separating this 4 as 2 into 2, and it is going to be divided by dc minus dr by 2, where this dc by dr can be equal to E is equal to E max. That is, dc minus dr by 2 is the condition where we are going to have the maximum eccentricity. Thus, I can say that shaded area is going to give us the Vd max, and therefore Vd max is going to be calculated along with the shaded area into the width of the rotor or the vane. Now, when you are going to multiply the shaded area along with the width, it is going to give you the maximum volumetric discharge. Then the actual volumetric discharge was going to occur when V is equal to E max. That is, when it is completely eccentric, it will gives you the maximum discharge. That is called as actual volumetric displacement. That is going to be calculated by this formula. Now, how this is going to work, you can understand. When E is equal to 0, when the center of the camering and the rotor are concentric, which you can observe in this figure, then the theoretical displacement is going to be 0. That is, Vd is equal to 0. That is, no pumping is going to take place. That is, when there is a eccentricity, then only pumping is going to take place. You have to remember this concept very clearly. Then coming to the theoretical discharge, it is given by the formula. It is a product of theoretical discharge and the speed. Mathematically, it is Vd into N, where Vd is going to be the formula what we have taken here, pi by 4, 2 into E into dc plus dr into W into N, which will be meter cube per minute. If you want to convert into second, divide this formula divided by 60, it will become meter cube per second. So by this, I would like to conclude this session because it is going to stop the time allotted. And thanks for your patience listening to the session. If you have any sort of doubts, feel free to use the comment section for the further discussion. I will answer all your questions related to the topics covered in the session. And don't forget to like, share, and subscribe. Have a great day. Signing off, yours lovingly, Vijay Tavardhan.